Okay, good afternoon. This is Ahmed from University of Oulu. And the presentation will be regarding the optimization of thermomechanically controlled processing parameters to enhance the mechanical properties of 201LN stainless steel for cryogenic applications. Okay, and quickly I will go through very short and quick introduction, then introducing the Tmcp Kleber schedules or samples, then the results out of these samples, then going to production or plates in the production scale, then conclusions. So regarding the austenitic stainless steel, in general, they are promising grades of steel for cryogenic applications, and particularly we are targeting in this research storage tanks for liquefied hydrogen and liquefied natural gas. And this is because the high strength and ductility for this stainless steel, type of stainless steel, austenitic stainless steel, low temperature performance, corrosion resistance, and weldability. And specifically, if we are talking regarding 201LN, we will have one or two actually advantage, but the main advantage would be the cost effective because of the elements. I'll show it. And then, of course, the toughness and ductility at the cryogenic temperatures. Okay, so the study aim or focus is optimizing the Tmcp parameters for these kind of steels to enhance the mechanical properties. So this is the general scope of our study. And also the research steps we have taken. So first, producing samples for to simulate it using Kleber. We have selected here 6 schedules. I'm going to show them in the next slide. Then doing some microstructure hardness to characterize those results from Kleber. Then finally, selecting the final parameters and producing it in a semi-industrial scale rolling machine, and then testing the tensile properties and see the enhancement for those kind of parameters. Initially, we produced 80 kilograms ingots, then subsequently hot rolled with roughing or reaching the thickness of 60 millimeters. Then this thick plate material is the starting material for all the Tmcp samples. And of course, after that, the Tmcp plates. And as specified in the EN standard, this is the composition or the actual composition of 201LN used. And here we could find the almost at the higher limit of manganese content for this 201L. Yeah, so moving to the Tmcp samples. As I mentioned that there is 6 schedules, so you can find it here. A, we can forget it now. So we have from 1 to 6, those are the schedules, and the schedules are done in 2 hit compression, first and second compression. So the first compression for all of the schedules is 1100, and the true strain is 0.29. Then for the first schedule A, named A, this was used as a reference, or so we don't have second compression here, it's just the first. So this is like the result from the first compression. The temperatures here are 850, 900, 950, and 1000. And also it's worth mentioning, we have the second schedule for all of the schedules are of true strain 0.25. And out of, to see the effect of longer time holding, from this curve, we can see that we have holding time of 120 seconds for homogenization, then going for the first compression, then cooling at a cooling rate of 3 degrees Celsius per second, then getting the second head, then using airflow as an air cooling inside the Kleber simulation. All of our characterization was done at the mid section of our samples, and for further investigation, all the samples were prepared final step with electropolishing, so we could remove from 100 to 150 microns of the layer, and of course we're going to avoid any stress-induced layers through the mechanical or the traditional mechanical polishing preparation. Okay, moving to the results from the TMCP samples. This is the hardness measurements, and this point is the first compression. So this is point A. And we could see that all of the schedules from the second head, we have increased hardness. And this point, we have, there was one schedule, I'm sorry, forgot to mention here. Yeah, at this point, we have one very slow cooling. So it's controlled cooling of 1 degree Celsius. So this is also one important point, which is here. So at the same temperature of 900, we have 2 points, one which is slowly cooled, and one which is almost quenched or air quenched. And this is the 60 with the holding time. So hardness here, it decreased with the longer cooling rate, but we have this weird behavior of increased hardness for the holding time or longer holding time, and this may be due to some recrystallization happened or something inside, but still we are investigating more regarding this point. Moving forward with the optical microscopy, we, according to our investigation, we found that we have a mix between the statically recrystallized and deformed grains. So to have an accurate estimation of the grain size, we actually compared both methods of arithmetic mean and this area weighted size grain size. So we used some image processing incorporated with machine learning to accurately measure the grain size, and then we could have accurate data to each single grain, and then accordingly we could apply the area weighted grain size. And for the results, we have almost the same trends, but I would trust more for these results, the area weighted grain size, or this is what was recommended for this kind of study. And also here from the results, we can see that optimum, the temperature, so the grain size, the grain size at 850 when we are holding more time, before cooling, there is a grain growth happening. So that's the deviation here. And for the slow cooling also, we have relatively higher grain size. But for all schedules, the grain size was much lower than the initial condition, which is the A condition I mentioned in the beginning. Moving to the EPSD, we have selective specimens for 900 air-cooled and 900 slow cooling or controlled cooling of 1 degree Celsius and 950 with air cooling. And the only thing to mention here that there is here strain-free grains with this slow cooling. So this could explain why we have lower hardness for this specific case. Also, we had the average grain size, and just to mention that this is still a fully austenitic out of this TMCP sample, so it's fully austenitic, despite those small fractions open 0.06, so maybe kind of error. And also for the random texture, it was random textured except for the this is the y direction, which actually is the compression direction. So because of the pancakes, so there is this effect. Okay, so moving to the TMCP plates. From the previous study, we concluded that the optimized the schedule, and the schedule was selected to have 6 passes were above the TNR, which is the recrystallization temperature. And then after the 6th pass, we have controlled pause for reaching the temperature below the TNR, which was around 1030 degrees Celsius, and then using 2 final passes below TNR of total reduction of 29%, and the final quenching temperature was below, slightly below 900. Exactly, it was 890 for the final quenching step. We produced these samples from the TMCP plates according to the ISO. And we also produced one solution, a annealed plate for a reference or a comparison. And we could see here from the results that if we take the solution annealed case as a reference, so we have an enhancement of 72% in the yield strength. So the yield strength reached 673 and the ultimate reached 860 with a relatively enhancement of 23%. And final for the tensile samples for the fractography. So in the beginning, we could see clearly. So this is the Tmcp plates or the sample from the Tmcp plates, and this is a solution annealed, and this is a relative scale. So we could see here that the ductility or the area reduction in area is quite higher. Microvoids and shear zones are quite clear, and SEM image also show the dimples, but we have here in the shear zone, we have deep dimples for the solution annealed and shallow for the Tmcp plates, which is quite common features for this kind of failure. And this is like a zoomed in SEM. So for conclusions, we were able to achieve enhanced mechanical properties for this 201LN stainless steel. The second pass of 900 results in partial recrystallization, despite this temperature is below the TNR, and general increase in hardness for the second compression. Final Tmcp production enhanced yield strength was 72 and the ultimate with almost 23. And we are expecting that this could be an enhancement that could be potential for cryogenic applications. Finally, I would like to acknowledge RFCS. So this is the Austrom project, and those are all the partners contributing in this work. And please, if you need to contact, so for any further collaboration, and thank you.